Hi judges, my name is Jeff Mao and my project is on toxicity detection AI with TensorFlow and the generalized neural network. My mentors are Robert Foreman and Xiaoming Wang. So the project goals for this specific poster was to implement a toxicity detection model to detect toxic language in online environments such as Instagram, Snapchat, social media in general, using TensorFlow, Keras, and GNN. The more specific goals I had in mind for this were to establish a GNN cluster on Azure Cloud, classify toxic language based on composition, so if it was extremely toxic, if it was hate-based, if it was racial, etc. Next, I wanted to create a proof of concept in Python to see if this idea would work. Following that, I would transform and move all the training data and the model from Python to Azure Kubernetes and GNN. Next, I would set up and modify the tensor layers using GNN Python embeds, and finally, I'd create a UI with Roxy queries on ECL Watch. That isn't the last goal though, because there is one I'm still working on, which is to write a white paper on the benefits of the generalized neural network over conventional neural networks such as RNN and CNN. So why toxicity detection? Well, the trend of online harassment, also known as cyberbullying, has exponentially grown throughout the years since the creation of the internet, and it has been linked as a major factor in depression and suicidal thought and poor self-esteem in teens. And as a person that has experienced cyberbullying, and with peers that have as well, I would like to curb this. Now, how can toxicity detection help? Well, by providing a means to detect harmful language, the toxicity detection model can give admins and site owners the methods to classify and handle specific harassment on their apps and services. The model can be used client-side to prevent toxic language from reaching the user, and all in all, the removal of such toxic language will promote a healthier online environment for all users. Next, we move on to the neural networks and the architecture. So generally there are two common neural networks which are known as RNN and CNN. So RNN is the recurrent neural network, which is an artificial neural network where connections between nodes are formed through a sequence. Basically, neural networks, blocks and cells, also known as nodes, are linked together like chains, and each block passes a message to a successor. Now, this architecture allows an RNN model to retain previous information and act like short-term memory. On the other hand, we have CNN, which is a deep feed-forward artificial neural network where the connection between nodes does not form a cycle. CNNs are organized by stacks of distinct layers that transform the input value, or volumes, into a distinct output volume through differentiable functions. This is extremely useful for images, but not as useful when dealing with natural language processing, which toxicity detection is all about. And as you can see, because of RNN's ability to retain previous information, it is very beneficial for textual data, as text is sequential, and you need to read the entire sentence in context to understand whether it is toxic or not. Next, we're going to move on to word embeddings. Though you and I can understand words, our machine learning algorithm unfortunately cannot. That's why we have to display it as a separate vector, which is displayed as a numerical function. Computers are very good at understanding numbers and calculations, but they're not so good at understanding the human language. So that's why we have to translate it into a numerical representation. And this representation is in the form of a vector known as a word embedding. And over here we have the specific steps. I'm not going to go too in depth here, but essentially all you have to do is convert each element from a list of strings into a list of integers through word embeddings and sequences, create the features and label from those sequences, build the long short-term memory model with embedding LSTM and dense layers, load in the pre-trained embeddings, train the model to predict the next work in sequence, and finally make the predictions by passing in the starting sequence. Next, we move on to the GNN implementation. The generalized neural network is a paralleled interface that provides machine learning developers the parallel processing power that HPCC systems offers and the neural capabilities of Keras and TensorFlow API. The bundle leverages the ECL language to provide the HPCC processing power, which is great in theory, but unfortunately for me, I had to migrate my Python code over to GNN, which required several changes to make it all compatible. So the first change we're going to talk about here is data. Arguably, it's the most important one, and it took the longest time to implement correctly. In its original form, on the Python side, the training data was presented in a CSV file with each column occupied by a phrase and then followed by several numbers classifying whether it was toxic or not and giving specific numbers for each classification. So say, for example, if it was like racially based or hate based, etc., it would give a number either 0 or 1. 1 representing the most toxic rating that you could get, and 0 representing not toxic at all. After that, since the GNN only takes numerical inputs, the word embeddings were given indexes so they could be called by the text matrix. Next, the text was separated by space and then converted into indexes, which represented the numerical word vector representations. So essentially, instead of having a single CSV file, they were separated into 3 files, which first one being sentence ID set. It contained each sentence, which had all of the words in sequence form, so it was all numbers. And these sequences were basically the indexes of the word ID set. The word ID set was, oh, sorry, I accidentally clicked off, but the word ID set contained each word vector, which was identified by an ID. And this ID was used in the sentence ID set in order to identify which word vector went with which word. And finally, we have the weight ID set, which corresponds with the sentence ID set, giving the sentence ID a weight, basically a label, identifying if it's toxic or not. Now, this is only for training. Next, the second part that I had to edit was through the Keras layers. For the most part, they remained unchanged from the original proof of concept. However, there were a few embedding layers that were dropped, such as the input shape and embedding layer, because that was all defined through the ECL code. Moreover, the output of the GNNI implementation had to be changed because it only returned a single integer instead of several, and that single integer only had 2 possibilities, a 0 or 1. But because of the Python embedding layers that GNN provides, this transformation of layers was very simple. Now, after I ran a few tests comparing the GNN model with the RNN model, I came up with a few interesting results. Let me go back in there. So for the RNN model, you could see that the loss was 0.0425 with an accuracy of 99%, rounded up, whereas on GNN, the loss was 0.19 and accuracy of 93%. Now, it might seem like the RNN model is ahead, and well, that's true. But you have to remember the RNN model took 5 hours to train, whereas the GNN model only took 20 minutes. And it trained with the same amount of sentences and same amount of data. So giving the GNN model an equal amount of time, or giving it more time and more resources, would undoubtedly either match the RNN model or improve upon the numbers that the RNN model displayed. So now we can go over the benefit of GNN. The GNN bundle leverages HPCC's open source big data solution, which gives developers more flexibility and better tools for dealing with machine learning algorithms. So, for example, speed. In my own benchmarks, I could see that the GNN model was 15 times faster than conventional neural networks. It's also cost effective because jobs are spread across multiple nodes, decreasing the overall cost. It's very scalable because it's done through HPCC, and there are Docker images through GNN or through Docker Hub for GNN, and I can scale it easily on any sort of cloud platform. Also very flexible because I can import my Keras TensorFlow layers from Python through embeds or utilize ECL code to train and build models. And it's also very efficient. the GNN tensor model allows users to efficiently encode, decode, and manipulate tensors within ACL. Now we get to the conclusion. This was the most complicated project that I've ever taken on, and I would like to share the experiences and my final thoughts on it. The GNN bundle is an extremely versatile and useful tool for machine learning. Its ability to spread work units across multiple nodes while retaining memory makes it the perfect candidate for natural language processing. Moreover, its speed and efficiency is unrivaled. And this all improves accuracy and decreases cost, which is essential for all developers and large corporations. All in all, the GNN toxicity detection model outshone the RNN model and proved itself as a strong alternative to other neural networks, and I'm excited to see what HPCC systems will offer in the future with GNN. Finally, I have a few resources. Here I have the Keras API. Here's the GitHub repository for my toxicity detection model, and third is my blog on everything that I went through, and it'll go through this poster, but much more in depth. Thank you for listening to my presentation. I appreciated this internship opportunity and would love to talk with all of you guys again.